So I have the pleasure and honor to introduce my dear colleague and friend, Marco Dentz. And he was too kind that just right now he shrinked his slide. So he made it a bit shorter of speak. I mean, this is one of the many reasons he's such a dear colleague in the community. So Marco is professor at the Institute of Environmental Assessment and Water Research of the Spanish National Research Council in Barcelona. I guess they have better weather than we have here. Research in his group focuses on hydrodynamics of hydrodynamic flow and transport and the quantitative understanding of flow, mixing, and reactive transport phenomena from the pore to the regional scale in heterogeneous, porous, and fractured media. He received a doctor degree from Heidelberg University in 2000 after a postdoctoral study at the Weizmann Institute of Science. He joined the Technical University of Catalonia in Barcelona. Since 2009, he has been a full professor at the Spanish National Research Center as well. He received in 2021 Interpor Medal for porous media research for his contribution on mixing science in porous media. Marco, we are very much looking forward to hearing your lecture, and thanks very much for coming over from sunny Barcelona to sunny Delft.
Thank you very much, Hadi. Thank you very much for inviting me again to this great summer school. And thank you very much for this very kind introduction. So I was asked to deliver a talk on mixing and dispersion in underground hydrogen storage. So it's mixing and dispersion, so you see these two things are not necessarily the same. So the outline of my talk is, for the next 1.5 hours. So first, what is mixing? Then about mixing in porous media, mixing in the context of hydrogen storage. And then some things about the concepts of hydrodynamic dispersion and how to separate between mixing and dispersion or mixing and spreading. So first, what is mixing? So mixing phenomenologically is a process that homogenizes initially segregated constituents. No, it's very intuitive. That's what all of us do every day, more or less. So mixing increases the volume that is occupied by a substance. It decreases peak concentrations, very important when you have contamination. And mixing facilitates chemical reactions, so another important action. So here you have just an illustration of mixing of two types of dyes. And the mixing is helped here by stirring. So I will get to this in a moment. So if you think about mixing, maybe you think about diffusion. Now, diffusion is a process that increases the volume occupied by a substance, but diffusion is typically very, very slow. Now, diffusion coefficients are typically on the order of 10 to the minus 9 meters squared per second in a liquid, maybe chlorine in a liquid. So if you would wait in the morning for milk or sugar to diffuse in your coffee, you would wait quite a long time. So what you do is you help it by stirring. Now, so stirring, when you stir your coffee, you're creating filaments of the substance that you want to mix. So the length of these filaments grows exponentially. So you're creating a space-filling structure in your vessel. So these filaments, they fold back to each other, and what you do is you approximate them so diffusion can act very efficiently because it's very good on small distances. So on the mixing time, is actually the time that you need to stir plus the time that you need to diffuse. Yeah? So it's much, much faster than 1 day that you would need to wait by diffusion. So mixing, so this is about mixing in fluids. So, but we are dealing with porous media. So there the things are a little bit different because, you know, we have multiscale heterogeneity. So a fluid is permeating through the porous medium. So we're looking at different scales. We have a pore scale here. So then we have, say, gravel type heterogeneous media. We have fractured media. We have heterogeneities from the micrometer scale or even nanometer scale to the kilometer scale. So how does mixing in porous media work? First, we need a flow. No? We have our substance dissolved in the flow. And on the pore scale, we are permeating a fluid through the pore scale to pore space. And we are creating quite a complex flow structure. You have high velocities, maybe narrow pores, or in large pores, depending on the connectivity. And if we put say a line source into this, what we get is a very distorted distribution, a complex distribution of the concentration. And similarly, similar things we observe on the continuum scale or the Darcy scale. So here, if a medium is characterized by a spatial distribution of hydraulic conductivity, and this would be an initial line source that disperses out. Now, so we have two things. We have dispersion, and we have mixing. Two things are not the same. Now, the mixing is essentially the width of this front, and the dispersion is this distortion of the line. So the processes basically that we have is we have stirring, like in our vessel, but the stirring is done by the porous medium. No? As the fluid permeates through it, the medium itself stirs the solute. The filamentary structure that is created is not space filling necessarily. So space filling structure you create if you have chaotic mixing. But we do not necessarily have chaotic mixing in a porous medium. So for example, a typical spatial distance between the filamentary would be a characteristic length scale of the medium, which could be the correlation length of your log K field, or which would be a grain size when you're on the pore scale. So we are not space filling, but still diffusion has to act. So the diffusion time to homogenize filaments is much bigger than what we have in this nicely chaotically stirred vessel. So the scales that are relevant is the characteristic heterogeneity length scale, micrometers to millimeters on the pore scale, and meters to hundreds of meters on the continuum scale. So a characteristic advection time is the characteristic scale divided by the mean velocity. So this would be a stirring time scale, which is, when you do like this in your coffee, this is very fast. But if you have to wait on a continuum scale, you have meters of your characteristic length scale, and you have maybe meters per day, centimeters per day for your flow velocity. This is quite a long stirring time scale, and the characteristic diffusion time can be even larger. No? Because the pore scale, we are millimeters. On the continuum scale, we are talking about meters. So they are very, very long time scales. So Pecklin numbers on the pore scale, now Pecklin number is a very relevant non-dimensional number, which compares diffusive and advective transport mechanisms. Or here, let's say diffusive mixing versus stirring. On the pore scale, larger or greater than 1, and on the reservoir scale, they are typically much, much larger than 1. Yeah? So on the reservoir scale, we are typically not well mixed. Yeah? So now mixing in UHS, just some background. I mean, there has been a lot of presentations and discussions about processes. So specifically for mixing, so the phenomenon we have is we have the displacement of a reservoir fluid or cushion gas by injected hydrogen. This is the fundamental process. We have a heterogeneous medium typically, as I said, on multiple scales. So mixing is relevant for mixing of hydrogen with the cushion gas, with the reservoir fluid. Mixing of the cushion gas with the reservoir fluid, it's another mixing process. And then, of course, if you have reactions, biogeochemical reactions, you need to mix the hydrogen with another constituent, either with methane or with CO2 or with the fluid. So the mechanisms of mixing, just a little summary. We have diffusion, number one most important mechanism, but we need to help it a little bit to be efficient. Then we have the medium and the flow heterogeneity, which stirs our mixture. And then come already some upscaled concepts, which is mechanical dispersion. I will talk about this a little bit later. So another mechanism is viscous fingering. It's another stirring mechanism. So if you have flow instability. And convection, similarly. Capillary flow, another mechanism. that is relevant, and temporal variability, of course, because we inject and produce. So temporal variability, this would be maybe the closest that you can get to the stirring of a vessel. So what we need is we need a realistic quantification of mixing and of these processes. So just some examples. So we have a displacement process. There is gas-gas displacement that you see here of a paper by Feldman et al. 2016. And so which is basically miscible displacement. Then you can have a two-phase displacement, which is poorly miscible, let's say immiscible, would be gas-water. So mixing from viscous fingering, there have been quite some studies in the literature. This is just one example of a paper by Birantja et al. So they studied miscible viscous fingering. Now you have a low viscosity fluid that you inject in a high viscosity fluid. The two mix. You get viscous fingering. And so this is something that you want to avoid at all costs in hydrogen storage. So, but what they investigated is actually enhancement of mixing. So due to you get enhanced interfacial area, so you have more surface to dissolve. And they found there's an optimal mixing as a function of the viscosity contrast. So this would be, so you want to avoid this at all costs. No? And another example is buoyancy. Now often you get a gravity override, because you have a hydrogen floating on top in a typical storage situation. And so what has been found in literature is that buoyancy typically suppresses mixing, because you have either an upwelling fluid or you have a fluid which is a little bit denser on top. And what this does is it compresses an interface and it suppresses mixing. Then, so typically the type of scenarios you're interested in is periodic driving. Now you inject, you let it maybe rest, then you extract, and you're interested in reversibility. So optimal would be you have 100% reversibility of your injection process. So to recover as much as possible. But then what you have is in gas-water displacement, residual trapping. In the pore space, there is hysteresis, was mentioned a few times, dissolution of hydrogen at the interface with the other fluid or at the interface with the cap rock, and then diffusion in the other in the reservoir fluid, for example. And in gas-gas displacement, there is gas mixing, of course, and biogeochemical reactions. So here, this is simply some preliminary study that was looking at injection in an anticline. It's a two-phase displacement exercise of hydrogen into brine. It's a heterogeneous medium, so this is a permeability map. And so this is the distribution of hydrogen after, I think after the first cycle. So you see the distribution is very heterogeneous. And so the fingers that you see are actually heterogeneity fingering. So there's no viscous fingering here. It's just the heterogeneity of the medium. And so what is found is that the cycle by which you inject is important regarding the recoverability. So you always lose something. Yeah? Even if you have a homogeneous medium, two-phase displacement, it's a simple Buckley-Leverett situation, no capillarity, there is irreversibility in your equations due to nonlinearity. And so then you find also heterogeneity plays an important role for recoverability. So what do all of these examples that I showed you have in common and are relevant, and what is relevant for mixing is that we have to consider mass transfer across deformed interfaces. So in viscous fingering, you have a deformed interface. Heterogeneity causes deformed interfaces. So what we want to know is what is the mixing volume? No? What is the amount of hydrogen that is going to be, let's say, that is lost by mixing or that is available for reaction? So we want to estimate this VM mixing volume. Would be porosity times the gas saturation times the mass fraction in the gas times the saturation of the liquid phase times the mass fraction in the liquid phase times the mixing volume. No? So mixing volume is a key character, a key quantity here, so the mixing volume could be quantified by the area and the thickness of this mixing interface. So it also quantifies that the area that is swept by the interface. So how can we quantify it? And how can we quantify the impact of, so here I want to focus on spatial heterogeneity. So the concept that many of you have heard about is hydrodynamic dispersion. So because this is a concept, so why people use this in porous media or in hydrogeology is because it's very similar to diffusion, which is something that we know very well. So before going into this, first let's define a little bit the microscale model that I want to consider. So I want to consider an advection diffusion or advection dispersion equation. This is my microscale model. Microscale means I'm on a scale that is lower than my characteristic heterogeneity scale, which would be Pore scale or correlation scale on the continuum scale. So on the Pore scale, this is the scale 10 to the minus 5, 10 to the minus 3 meters. Flow is governed by Navier-Stokes equation. Diffusion in the liquid phase by the Einstein formula. No, diffusion coefficient is given by temperature, viscosity of the host fluid, size of the molecule. These are the typical values that you have for hydrogen in the liquid, and then we have diffusion in the gas phase. It's a little bit more complicated. Maybe you will have to use Stefan Maxwell theory, and you get a nonlinear dependence of the diffusion coefficient on the partial pressures of the other constituents. On the continuum scale, this is the typical heterogeneity scale, 1 to 100 meters. Flow is given by Darcy equation and all variants of it for variable density multiphase flow. And then we have already an upscale concept. This is the dispersion coefficient. It's the concept of dispersion, so the velocity fluctuations that you have on a Pore scale, you basically lump into a dispersion coefficient. It has this form. It depends on the velocity, no? On the local velocity. No? So this already tells you if your velocity is 0, there is no dispersion. So this happens, you inject, then you have to wait because you want to store it. And if you, in your simulator you use dispersion, then this dispersive flux is totally overestimating what is actually happening in the resting phase. No? And the diffusion also on the continuum scale in the liquid and gas phase is given by Fick's law or by another model, which is called a dusty gas model. I cannot go into details. So now, just to recall, so this is what, let's say, the microscale transport looks like. No? On the Pore scale, we have this type of situation, dispersion plus mixing, and then the Darcy scale. So how can we quantify this mixing interface? And then to estimate hydrodynamic dispersion, what people did is they said, okay, look, I'm going to measure a breakthrough curve, no? And concentration in effluent. There is a poster here by Sam Kobasi who is doing this. Or people have measured, like here at the Cape Cod site, they have measured concentration plumes on the field scale and then calculated dispersion coefficients from spatial moments. And what is found consistently is that dispersion has a scale effect. So depending on the scale on which you measure it, dispersion is becoming bigger. No? So this was a big, let's say, conundrum in the 70s. And then the question was, how can one explain this? So people said, okay, let's go to the diffusion analogy. No? What is a Brownian particle doing that is suspended in the fluid? Is making some erratic motion. No? So it has a velocity that fluctuates in time because it collides with the molecules of the liquid, no? With the water molecules. I said, okay, but here what I have in the porous medium looks very similar now because when I look at particle trajectories, they are quite random, no? Because I have a heterogeneous medium structure. And I said, maybe I can quantify this in the same way I quantify diffusion. And I said, okay, let's look at this type of a Langemann equation, or Langemann equation, the mother of all stochastic equations, what's used by Einstein, Smoluchowski, Langemann to quantify Brownian motion. And I said, okay, I have in the porous medium a mean velocity, and I have fluctuations about this mean. No? It's like a Brownian particle that has velocity fluctuations. So now what I need to do is I just have to characterize these velocity fluctuations. and I can get an estimate for dispersion. So this is a very, very useful formula. It's called the Taylor-Kubo-Green formula that relates your hydrodynamic dispersion with the velocity variance of your Eulerian velocity field and the characteristic correlation scale. And this defines the dispersivity, mechanical dispersion. And so with this simple concept, we can go and explain the scale effect of dispersion. So number one, we say that if this correlation time is very, very large, I really have a Brownian motion type of situation. This is the idea. And then I can write down an upscaled equation of this type. I have a mean velocity, and now all the fluctuations, all these random fluctuations, I put into a hydrodynamic dispersion coefficient. So now when I do upscaling from the pore to the continuum scale, I have to think, okay, what is a characteristic correlation scale? It's just the pore length, no, characteristic length scale, divided by mean velocity. So this would be my decorrelation time. The velocity variance that I have on the pore scale, or in general, is just the mean velocity squared. Now I take this Taylor-Green-Kubo formula, and I get immediately an expression for the dispersivity, mechanical dispersion. Is probably many of you know, is simply the pore length. No? This is your measure for mechanical dispersion. And when I go to the field scale, I do a similar exercise. Decorrelation length is basically your characteristic length scale. No, it's the correlation scale of your hydraulic conductivity divided by the mean Darcy velocity, and then the velocity variance. So this is a result by Gelheim, Exnes, Dagan, Neumann. Using perturbation theory is simply the mean velocity squared times the variance of your log K field. So and then you get another estimate for dispersion, which is this time proportional to the correlation scale of your hydraulic conductivity. You know? So now here you have your scale dependence. Now, depending on the scale you look at, you have different values. So now you say, perfect, this is a super result. Now I'm fully predictive because now I have related dispersion actually to measurable quantities, to material quantities of flow quantities. I don't have anything to fit. No? And what I have done is I have said I have this microscale heterogeneous object, and I represent it by a homogeneous medium, and all the fluctuations I put into dispersion. So I have decoupled advective displacement and dispersive mixing. My mixing volume, I can now quantify very easily, is simply the width of the mixing interface, which is hydrodynamic dispersion times the velocity times, so this is normally negligible, it's much smaller than dispersion, times the area of my interface. No? But now you have to think dispersion acts only during injection and production, does not act during the resting phase. So now, excellent, but there are of course some problems, as you may have anticipated. So one of them is upstream dispersion. I don't know whether you ever came across this, but if you want to model the displacement of one fluid by another, so here we would have a certain constant concentration here, zero concentration here. We want to displace this fluid. And now if we use the macro dispersion approach, this is the prediction that we would get. So this is a direct simulation in a heterogeneous K field. So you see you get back dispersion, and you greatly overestimate the actual mixing zone, right? So this is of course related to the fact that when you look at a dispersion coefficients they vary in time and vary in space. No? So when you are at very short time, so when you are here, your interface is basically zero width, no? Because you have not had time to experience heterogeneity. So macro dispersion coefficients evolve typically from the local value, diffusion or local scale dispersion, towards a macroscopic value. And this evolution takes a lot of time. Now, because you have seen the time scales, particularly on the reservoir scale, they are very long. So you can interpret this evolution either as an evolution in time or evolution in space, now as you move through the medium. So this is one set of problems with this approach. Another one is that we have separated advection and dispersion, but this is not always warranted. No? So here we have an example of a numerical experiment where we injected 5 blooms, and then we let them spread. No? So each of these blooms has its own center of mass velocity and its own spread. So at the end you get this heterogeneous distribution, and then we reverse the flow velocity, and what happens is, well, they all go back and align on the same line. No? So we have reversibility because we have an advective effect and an advective effect that essentially distorts, let's say, a line, but this is an effect that is reversible. No? If you have only advection, if there would be no diffusion or dispersion on the microscale model, this would be 100% reversible. No? And this brings us directly to the next point, which is how can we, 5 minutes? Okay, yeah, super. This is mixing versus spreading. No? So, and this is the standard definition using moments of hydrodynamic dispersion is you take your global distribution of a solute, and then you calculate the center of mass and the second moment, and then you can define the dispersion coefficient just as the rate of change of this second center of moment. And then what I just said, purely advective spreading. So this is a line that has 0 diffusion, 0 dispersion. It creates a very as it is transported through the medium, there is a very complex structure created, a complex laminar structure. But if you reverse this complex structure is reversed to a straight line. But if you let diffusion or local scale dispersion act, then you get a mix. No? So this is what I said before. You are stirring and you are helping your microscale mass transfer process to mix. So this is what's happening here. Yeah? So spreading is in general not mixing, no? And dispersion is not always mixing. No? Spreading is just this advective spreading, and dispersion is containing both processes, no? An advective stirring process plus microscale mass transfer. And so how can we separate these two? So there is one approach proposed by Peter Kidanidis in the 80s, which is called effective dispersion. So now we have this distorted line, so we have to realize that this is not a good measure for the mixing volume. What we should do is we should essentially quantify the actual mixing area. And for this, one defines effective dispersion coefficients, which means we are measuring the width, let's say, in the coordinate system that is going along with the line. And by this, we subtract center of mass fluctuations. So we are subtracting advective effects. And so this effective dispersion evolves then not on the advective timescale, but on a diffusion timescale, because this is the relevant small-scale physical mechanism now to achieve, let's say, large-scale dispersion. And so here you have an approximate expression that you could use in your simulator, for example, if you decide to adopt the concept of time-varying dispersion, for example. Yeah, so this is simply a comparison of the time evolution of this hydrodynamic dispersion, or what we call ensemble dispersion coefficient, and the effective dispersion coefficient. And another approach that you can use if you have strongly heterogeneous media or composite media almost, where you have inclusions. Now when you have highly heterogeneous medium, you sweep your medium with, let's say, with water with certain concentration of solute, and what you get is you get diffusion or advective trapping in low permeability inclusions. So you get these residual concentrations, for example, of hydrogen. And so the way to deal with this type of situations is you adopt a dual continuum approach. So you say you have a mobile continuum where you have advection and dispersion, but dispersion is well controlled in this because you don't have strong heterogeneity in the background. And then you have mass transfer between these low conductivity inclusions in the background. So this is by this term, this model by this term. So you have a memory function that is basically encoding all the physics of a mass transfer process, and this type of approaches have been used for solute transport and two-phase flow, for example. So this is an example, two-phase flow, I think, in a fractured medium. And the last approach is a very, so this is a newer approach that has been used in porous media maybe in the last 10 years, which is going back really to the physics of the mixing process that I mentioned already a few times, is the stirring and the mass transfer. So the stirring is creating a lamellar structure, and then these lamellar structures, they are coalescing by diffusive mass transfer between them, or local dispersion. And here the idea is to make an estimate for an interface length, for example. So this gives you an idea about the stirring. And what you typically have in porous media is that the interface length is growing with time. Of course, you don't have just a constant interface. No? So if you have fingering, you have viscous fingering, the interface grows linearly with time. The same happens when you have heterogeneity fingering. So, but here in general, you could have a power law increase of the interface length. So the interface length, so when you stretch something, no, to increase the length, so you are stretching it, and then you are compressing in the direction transverse to it. So compression of the interface always implies that you help diffusion, no? Because you are steepening a gradient. No? Diffusive mass transfer is proportional to a gradient. And so now you can estimate the mixing volume just by knowing the length of your interface and the width of the interface. Now the width of the interface is done by diffusion, for example, so you would get this estimate for the increase of the mixing volume. And this type of approaches, so very mechanical, let's say mechanical approaches that really go to the grain of the phenomenon. Later, in a later stage, so we have say this lamellar structure, then you get the lamella close to each other, and then they start coalescing, and this has been modeled by random aggregation type of models. No? So these approaches you can use for very, very complex systems, because the mechanisms are very fundamental. So even though you have a multi-component, multi-phase, heterogeneous system, oftentimes you can reduce the phenomenon to these processes, and you can make a relatively, you can obtain a good understanding of your system, and you can make an estimate for the mixing. And with this, the summary would be that, or let's say take-home message is stirring is not mixing. Huh? Yeah, macro dispersion typically overestimates the mixing volume, but really a lot. No? Particularly if you're interested in reactive transport modeling, this is a big problem. To use the macro dispersion approach, and then mixing and spreading, they need to be separated somehow. So I showed you, or I sketched some approaches of how to do this. Namely, effective dispersion or block effective dispersion is one, let's say, a very operational approach that you can use in your simulator. Multi-continuum models, a little bit more involved mathematically. And then these lamellar approaches, they give you a good idea about the physics of the mixing process. Thank you.
For questions, Chris?
Yeah, Chris Willis is from Shell. Thanks for the presentation, very nice. Would like to ask, do you have a feel for how the reservoir pressure and temperature would inhibit the advection aspect of the transport? Would it become more dispersive, maybe, at higher pressures?
Or in a way, the dependency of mixing and dispersion with pressure and temperature.
So, I mean, pressure and temperature, they would affect above all the diffusion. No? Gas diffusion or diffusion in the liquid. So the temperature by the Einstein formula is proportional to the diffusion coefficient. Or for gas diffusion, the higher the pressure, the lower the diffusion. But these are micro-scale mechanisms, of course. No? So when you look at the large-scale spread, this is a lot influenced by the spatial heterogeneity. And there, the important thing is the hydrodynamics. No? So the rate by which you inject, essentially. This is one thing. And then if you have flow instabilities, For example, viscous fingering, or maybe where gravity fingering typically you don't have because the less dense fluid floats on top.
Yeah. Thanks, Marco. Thanks for the very nice talk. So I have two questions. The first question is, for the pore scale, I see that you're using the Maxwell-Stefan description for getting the diffusion coefficient. And at the slightly larger scale, you're using the Fick's law for the diffusion coefficient. But if I understand correctly, both the Fick and the Maxwell-Stefan are dependent on the concentration. So why the choice of choosing two different descriptions?
No, so the thing is, so Fickian diffusion, so if you have a dilute setup, then you would use Fick. No? So in the Fickian framework, the diffusion coefficient is not dependent on concentration, so it's fully linear. No? So when you have gas diffusion, then you don't have a dilute system typically. No? And then, in fact, a diffusive flux can induce an advective flux, so there is a coupling. And then there is this. You have this Stefan Maxwell theory. I think is what I not 100% clear is how important this is to account for these nonlinear effects. But when you go to the poster of Sam Kubaisi, you see that actually it makes a difference. So in some posters, to give a short summary, he's measuring hydrodynamic dispersion. Hydrodynamic dispersion depends on the Peclet number. No? And the Peclet number depends, of course, on the molecular diffusion coefficient. And what he sees is that for different pressures of his sample, you get different dependence of the hydrodynamic dispersion coefficient from Peclet. And this, I think, can only be explained by using this type of Stefan Maxwell approach for the diffusion modeling. Yeah.
Okay. Yeah.
Bill. Bill Ross sent you Delft while I'm walking.
That's a very nice talk, and I'm guessing you were probably getting your measurements of mixing using some sort of particle tracking or something between streamlines. I would just warn the rest of us, we're probably going to be doing conventional numerical simulations, and for those, the numerical dispersion, simply the effective dispersion of effectively mixing on the grid block scale can really dominate. So let me just give an example. With a student, I was doing a study of the spreading of a temperature front, and we had this formula for upscaling the thermal dispersivity on a grid block scale, and I think definitely the formula was better. We compared it to not using the formula, and what happened was, first of all, if you didn't have an extraordinary grid refinement, the numerical dispersivity just kind of washed out all the other effects. And even if we used really small grid blocks, both estimates, the unscaled estimate was too small a dispersivity. The correct one we think was about right, but the numerical dispersion bumped them both up. So it actually made the unscaled one look better because it was artificially bumped towards the true value and made what I think was the better one look worse because it shot past the true value. So numerical effects can really be difficult to deal with.
Yes, no, fully agree. I mean, numerical dispersion, now if you're simulating in a heterogeneous environment, you have on the one hand, you have the numerical dispersion, which is on the order of your grid size times the mean velocity, no? Numerical dispersion. Then your hydrodynamic dispersion is mean velocity times the characteristic length scale. So you have to weigh now what discretization you use, because in the end, let's say if your discretization is smaller than the characteristic length scale, which it should be normally, no, because you want to resolve heterogeneity well, then I think your let's say your hydrodynamic dispersion effect is overwhelming the numerical dispersion.
Thanks a lot, Marco. And let's thank you one more time for this excellent lecture.